How the thermos works is, it protects your hot liquid from conduction and radiation. Convection is not a factor because the hot liquid doesn't cool itself off. The thermos is technically named a vacuum flask because it is made of a glass bottle inside another bottle separated by a vacuum. The purpose of this vacuum is to reduce the conduction between the bottle holding the liquid and any other surface that may absorb the heat. The thermos protects against radiation by the inner bottle being coated by silver, which prevents electromagnetic waves from passing through. The thermos was first invented by a Scottish scientist named Sir James Dewar. His field of study was cryogenics and needed a flask that would keep chemicals at a stable temperature. He put a glass bottle inside another glass bottle, sucked out the air in between, and discovered it worked. He hired a professional glassblower to make a sturdier version of what he had created and named it Dewar Flask in 1898. Seen here is silver, which prevents the radiation of heat by either reflecting or absorbing it. Silver acts the same way with all other electromagnetic waves.
The composition of a vacuum flask can vary almost as widely as its uses. The structure or exterior of the flask can be made of a metal, usually stainless steel, borosilicate glass, or plastic. The insulative properties also vary greatly. Consumer flasks function mainly by insulating the interior portion with a layer of foam or a layer of vacuum. In laboratory vacuum flasks, there is even more variation in the materials and structures used. Some laboratory vacuum flasks use a double chamber for extra insulative success. The inner walls are often made of glass and then covered with a thin layer of silver. The insulative layer surrounding that is either filled with a stable nitrogen and helium mixture or vacuum. Then there's another solid layer of either glass or another minimally conductive material. Surrounding that second layer is either a vacuum or a layer of nitrogen-helium mixture. This is all encased by a final solid layer of any of the previously mentioned materials. In 1892, Sir James Dewar, a Scottish research cryogenicist, designed a double brass chamber with an air evacuated layer to create a pseudo-vacuum between in order to keep his palladium samples at a constant temperature. The vacuum flask had scientific beginnings, but is now used also by the consumer population to keep meals warm on the go and drinks icy cold for hours on end. Dewar's expensive materials have been swapped for more economical substances in order to make his masterful technology accessible to the masses. The materials currently used for consumer products are both functional and cost-effective because they are easy to manipulate in the factory setting. The Thermos brand is a highly rated vacuum flask company which was founded in Germany in 1904 for consumer product. Stanley is another highly rated vacuum flask company based in the U.S., which was founded in 1913, also for consumer product. In the 60s and 70s, NASA used vacuum flasks for propellant tank storage in the Saturn missions. For scientific and experimental purposes, more research into superconductors could come out with even better materials for extending the time vacuum flasks can maintain very cold temperatures in the laboratory setting.
One material that is used in a thermos is borosilicate glass. This glass is also used in kitchen glassware, lab glassware, microscope lenses and slides, stage lights, thermometer glass, and it's also used as thermal insulation tiles in the space shuttles. Otto Schult, a German glassmaker and chemist in the 19th century, was the inventor of borosilicate glass. He was one of the first people to use boron compounds in the form of boron trioxide in glass to determine that it made the glass have increased resistance to chemicals and thermal shock. It was sold in 1893 in Europe and called Duran. Joe Littleton of Corning Glassworks introduced it to the U.S. in 1915 as Pyrex. It can now be found in various products that might be subjected to heat.
Borosilicate glass is produced by adding boron to a traditional melt of silica, sand, sodium carbonate, and lime, and heating the mixture to extremely high temperatures for long periods of time. The liquid material resulting from this process is then shaped by machines as the glass is too hot for humans to handle. Air is blown onto the glass from above while it is heated from below in order to ensure the strength of the glass. The glasses are then placed into a final mold and cooled down. Borosilicate glass has many uses in society due to its durability and resistance to chemical and thermal changes, as well as its elasticity. It is used to make Pyrex glasses and spotlights for stages, included in the production of armor-piercing ammunition. Borosilicate glass has largely impacted the cookware market. Borosilicate glass has a low coefficient of thermal expansion, meaning that the shape, area, and volume of the glass does not vary as the glass is subjected to temperature changes. Thus, the glass can keep things either hot or cold for hours, acting as an insulator. Borosilicate glass acts as an insulator and is tougher because it is engineered to withstand more extreme conditions than household soda lime glass. Borosilicate glass is engineered to be tougher than household glass so that it can be used in lab settings in which thermal, mechanical, and chemical conditions are harsher than household ones. Thus, if the glass is dropped, it is much less likely to break, and it is also more scratch resistant than soda lime glass.